So, good evening to all. Is the audio clear? And the video also? Tell me. Yes or no? Is it clear? Right. So in the previous class, we discussed some problems on permutation groups. So any queries for anybody on those topics? The concept of permutation groups, the order, what is meant by alternating group, even permutation, odd permutation, etc. To anyone? Tell me. Right. Then in today's session, we will discuss some small results based on alternating groups and the permutation groups. Then we shift our discussion towards the concept of cyclic groups. So once we finish with the cyclic groups, then we will cover the previous problems based on homomorphisms, cyclic groups, etc., etc. There we can conclude our discussion completely on group theory. Then we shift to the second module of abstract algebra, which is nothing but rings and fields. So after the completion of cyclic groups and doing some problem solving sessions, we shift our discussion towards the second module of abstract algebra, which is nothing but rings and fields. So it nearly takes around 20 classes for our discussion. Then abstract algebra will be completed, right? That is the upcoming class schedules. Is it clear to all? Say. Right? Now, as you mentioned, whenever we consider the symmetric group Sn of n symbols, the total number of permutations in Sn is nothing but n factorial, in which half of them are even permutations and the remaining are nothing but odd permutations. If you consider set of all even permutations into a set, we denote with the symbol an. And we call this set as alternating group. An. In fact, it will become a normal subgroup of Sn. This thing I already mentioned. An is nothing but a normal subgroup of Sn. Now, I just want to prove this result theoretically so that we will have a discussion on this. So, if you have proved this, it is a normal subgroup of Sn, then immediately you can say that order of An is nothing but half n factorial. Okay. So please take a note of this. Now we go with the concept, how to show that it is a normal subgroup. There are two different proofs. Both are equivalent. You can make use of any of them. So I will take the one which is given in the previous year papers and which is very easily understandable to everyone. So we have a group Sn with the operation circle. Now you take another group G comma dot where G is equal to 1 and minus 1. Here my intention is I want to construct a function from Sn to G which is a homomorphism as well as onto function. Why I am going to define that? Because I just want to make use of the fundamental theorem of homomorphism. So let me define a function that you define phi from Sn to G by phi of, whenever you take a permutation here, say f, its value will be either 1 or minus 1. You take 1 whenever it is an even permutation. You take minus 1 if the permutation is odd. So you define a function like this. Is it comfortable to understand? Tell me. Yes or no? Now, let us prove this or verify this whether it is a homomorphism or not. So you have to verify that phi of fg is equal to phi of f dot phi of g for all permutations f comma g belongs to Sn. So here, if you observe that since you can take any two permutations in Sn, you have different choices to choose them. You take both the permutations as even permutations, you take both of them as odd, or you can take the mixed type. So whatever the case you consider, to show that phi is a homomorphism, we have to verify phi satisfies this condition. Okay, so let us take the cases one after the other. So in the first case, you take them both f and g are even. Since they are even, from the definition of phi of f equal to 1 and phi of g equal to 1. Now tell me about the product. If you multiply the two permutations, what is the result? Is it even or odd? If I take the two permutations as even, what about the result? Is it even or odd? Even, right? So phi of fg, you consider this is nothing but 1 as per phi definition. So in the case 1, this condition is satisfied. Phi of fg is equal to phi of f dot phi of g. LHS and RHS have same values. Now you consider the second case that both are odd. Since both of them are odd, you have phi of f equal to minus 1, phi of g is equal to minus 1. Now what about the product? Is fg even permutation or odd permutation? If I take the two values as odd, what about the result? So it is even. We discussed it earlier. Therefore, phi of fg is equal to 1. So in second case also, this condition is satisfied. Phi of fg is equal to phi of f dot phi of g. So can you verify the third case? You take f as even and g is odd, and can you check that the condition gets satisfied by phi? Phi of fg is equal to phi of f dot phi of g. Please check on that. Is it satisfied or not satisfied? The third case. You take one value as even and one value as odd. All of you agree for this? Please reply. So, therefore, phi from Sn to G is a homomorphism. And by default, phi is onto. Because the codomain contains only two elements, 1 or -1. If you choose one, in the domain, you can take any even permutation. If you choose -1, you can take any odd permutation in the domain. So it is very easy. It's a trivial case. There is no need to prove onto here. So simply we mention that phi is an onto function clearly. So there is no need to show that phi is onto separately. So phi satisfies the conditions of fundamental theorem. Therefore, by fundamental theorem of homomorphism of groups, immediately you can say that Sn by kernel phi is isomorphic to G. Now let us evaluate what is this kernel. So if you write the kernel value from definition, it is set of all permutations in the domain such that whose image is equal to identity. In the codomain G. So this is equal to set of all permutations in the domain such that phi of f equal to 1. Because the identity element in the codomain is nothing but 1. So if you want to get 1, what must be the property satisfied by f? If you want to get the image 1, what could be f from a definition of phi? Even. So this is nothing but set of all permutations in Sn such that it must be an even permutation. So you are considering set of all even permutations as a result of the kernel. So the kernel is nothing but the set of all even permutations. Symbolically we write it as An. So from the very perspective of fundamental theorem, you can say that Sn by An is isomorphic to G. As and when you mention isomorphism, it is nothing but you have a bijection between the sets. Apart from homomorphism, you are saying that there is a bijection between the sets. So it means that on both sides, you will have the number of elements as equal. So from this, you can say that order of Sn by order of An equal to order of G. So here order is nothing but the cardinality of the set, the total number of elements you are considering. So this implies n factorial by order of An is equal to 2. because G contains only two elements. Therefore, from this point, you can say that order of n is equal to 1 by 2 n factorial. So, the set of all even permutations is nothing but half n factorial. Clear? Yes or no? And one more thing is, as you know, whenever you have a homomorphism, kernel is always a normal subgroup. You have proved that kernel F is a normal subgroup in the domain. You have proved that. So, since kernel is the normal subgroup, here kernel value is nothing but an. So, an is normal subgroup in Sn. So, at a time you have proved two results. One, an becomes the normal subgroup of Sn. Two, order of an is 1 by 2 n factorial. Okay? So, please take a note of this. Then we discuss the other things. After noting, please tell. Now, there is one important theorem in permutation groups, which we call it as Callis theorem. It is also given in one of the previous year papers. The statement says that every finite group is isomorphic to a permutation group. So this was the statement of Callis theorem. Please take a note of this. Then I will discuss the approach, what methodology here you are going to follow. Right. So here, the given hypothesis is every finite group. So first of all, let us start with a finite group that say G comma dot is a finite group. So as per the theorem, you have to show that G is isomorphic to a permutation group. So now the question is, what is the permutation group here? You just have to show that if you take a finite group, it must be isomorphic to some other group where it contains only permutations. Did you get the idea? Now, the whole procedure will be simplified in 3 steps. Step 1, whenever a group is there, first of all, I need to build a permutation. So for every group, immediately I should be able to build permutations or permutation. Second, the set of all permutations, how you have defined, must become a group. You have to show that. So for that set, you give a name, say G dash. In the third step, you have to show that the given group G is isomorphic to the new permutation group what we have constructed. So in 3 steps, we will prove the entire thing. So in the first stage, we have to build or we have to form a permutation. In the second stage, we need to construct a permutation group. At the third level, you need to bring an isomorphism between these two groups. Okay, all of you? The result seems to be lengthy, but the logic is very simple and very easy. There is no need to think more than this logic. So we go with the first level. So whenever you take a group G comma dot, you take an element A belongs to G. Since I want to build a permutation, it is nothing but a bijective function on the given set itself. So I am defining a function fa from G to G by fa of x is equal to ax. In other words, for every element in the group, I can able to build a permutation. So if I take the element 1, the corresponding permutation is f1. If I take the element as E, the corresponding permutation is fe. And how it is defined? So fa as defined as fa of x is equal to ax. It is nothing but you take any element in the group, you multiply the element with the suffix number what you have considered. Okay? Are you clear how the function goes well? Now, it is very easy to verify that it is a 1-1 function as well as onto. So let us try. So you take two elements such that fa of x is equal to fa of y. From this you can say ax equal to ay implies x equal to y using the cancellation law. So this you can take if and only if. So whenever elements or images are equal, corresponding elements are equal and vice versa. So at this point you can say that the function fa is 1-1 and well defined. Now to prove the onto property, so for every element in the codomain, we should have the corresponding pre-image here. Now you tell me any element here, you give a symbol for me. You give a symbol for me. Not a number, you give a symbol. A parameter, let me say, a variable. R. So if you take R in the codomain, here the corresponding pre-image is nothing but A inverse R. Why? Because if you apply the permutation fa of A inverse R, as per the definition of the function, it is A inverse R, applying associative law, A inverse R. So for every element in the codomain, this is the corresponding pre-image. So the pre-image varies from permutation to permutation. If you take the permutation as FA, pre-image is A inverse R. If you take the permutation as FB, the pre-image is B inverse R, like that. Did you get the logic? How the pre-image existed? That's all. So you have proved that it is a 1-1 function as well as onto function. Therefore, it is a permutation. So this is the way in building the permutation. So step level is completed, the first level. So any queries for anybody? Please take a note of that. Yeah, that is only for the permutation group. Yes, that means, okay, if you have a doubt, let me say, I want to say like this. If you have 3 here, the pre-image is nothing but A inverse 3. Clear? I want to generalize the concept. So to make that generalization, I am saying that you can give any value in the codomain, not a particular number, so that the understanding will be elaborate. You cannot stick on to a one number, because for every number you need to specify the pre-image, correct? Not only for one number. That's why I ask you for a symbol. That's it. Is everyone clear at the first part of the proof? Then I go to the second level. Right. So, in the second level, you need to form a permutation group. So, it means that I am writing a set G dash as it contains set of all permutations FA such that A belongs to G. Now, my claim is I have to prove that G dash with respect to composition of mappings is a group. So I have considered all the permutations into one set. Now my interest is I have to show that it is a group. So it is nothing but I have to verify closure law, associative law, identity and inverse. These 4 things I need to verify here. So if you go for the closure property, so you take 2 permutations FA and FB in G dash. Now please understand the pattern, how the permutation existed. For every element in G, corresponding permutation you are taking here. So immediately you can say that A and B are elements in G. So by closure law, A dot B belongs to G. Now you consider FA dot FB at any point X. Because our intention is, if you consider 2 permutations, the product of them is also a permutation that also will belong to G dash, that you need to show under the closure law criteria. So it is nothing but FA of FB of X equals to FA of, the definition is BX. Again, the definition is A into BX. Again, you can read it as ABX. So in a short manner, you can write like this. So at this point, you can say FA dot FB equal to FAB. It means that whenever you consider two permutations, the product is nothing but the permutation obtained corresponding to the elements product. A dot B will come here. So if you want to show that, let me say I have two functions with me, F and G. Now the question is, if you want to say that these two functions are same or equal, how do we verify? I have given two functions for you and I have asked you to verify that whether f equal to g or not. Then what basis you can confirm that they are equal? Everyone, please respond. If I have given two functions, so here elements are equal means the images are equal when you substitute the functions. It means you have to check that f of x equal to g of x for all x. Then only you can say that the functions are equivalent. F equal to g, isn't it? There is one more thing that for the functions, domain and codomain both are same. It means that f and g both must be defined on the same sets. If f is a function from a to b, g also must be a function from a to b. Domain and codomain must be same and corresponding images must be same. In that case only we confirm that these two are equivalent. Similarly, if you want to say that FA dot FB is equal to FAB, you have to ensure that domain codomain are same and corresponding images are same. That's why I have calculated FA dot FB at x. So you are calculating image of x for FA FB and image of x for FAB. Since these two are equal, so I am confirming that these two functions are equal. Okay? The underlined idea is that. Are you getting the context? Right. And closure law is verified here and there is no need to verify associative law. Why? Because composition of mappings is always associative. So you can say that F circle G circle H is equal to F circle G circle H. It is true for any functions. So here there is no need to verify associative law. So I just need to go for two things, that is identity and inverse. Let us verify them. So if you think about identity, so for any permutation in G dash, since E is identity element in the group, corresponding permutation FE belongs to G dash and FA dot FE is equal to FAE equal to FA. So FE is identity permutation. Please check on the procedure. Any doubts you can ask. So did you understand how identity is verified here? For any permutation FA in G dash, corresponding identity permutation is FE, because if you multiply FA and FE, again you are getting FA, the same element you are considering. Okay? And coming for the inverse part, so if you take any permutation FA, immediately the suffix element belong to the group G. So immediately you can say that A inverse belongs to G because G is the group. So as per the definition, F A inverse belong to G dash. Because how the permutation group is defined? For every element in G, corresponding permutation will be here. So if A belongs to G, A inverse belongs to G, so corresponding permutation is F A inverse, it will belong to G dash. So the inverse of FA is FA inverse, because on the product it is FA inverse, nothing but FE. So FA inverse is the inverse of FA in the set G dash. Therefore, G dash is a permutation group. That is the conclusion for the second part. Please check. After noting, please tell. Is that clear for all? So I have completed 2 levels in the proof. The third level is we need to build an isomorphism between G and G dash. So I am defining a function phi from G to G dash by phi of. Now please understand that G is a group, contains elements only. G dash is a permutation group, it contains permutations only. So whenever you take an element A here, you are pairing that with the permutation FA. So this is the mapping you define. And obviously it will become the isomorphism. So if you have a doubt, so let A comma B belongs to G such that phi of A is equal to phi of B, implies FA equal to FB. Therefore, phi is 1, 1 and well defined, and clearly it is onto. Because if you take any permutation FA here, automatically A is the pre-image, because you have constructed the G dash in such a way like that. And if you talk homomorphism, you say phi of AB, it is FAB. So FA dot FB, so phi of A dot phi of B. So this is for homomorphism, this is for onto, this is for 1, 1. So it is clearly an isomorphism. So we can immediately say that G and G dash both are isomorphic. G and G dash both are isomorphic. You take a note of that. After noting, please tell. This is the proof of Cauchy's theorem. Any questions, any doubts for anybody for this Cauchy's theorem? Say. Right. Now, if you want the problematic approach over this concept, let us take some problems. Let me say, suppose we have taken the group G is equal to 1 minus 1 I minus I. Now the question is, what is the permutation group which is isomorphic to G? Now tell me how many numbers are there in G? I mean, how many elements in G? 4. So if you want to construct a permutation group, it also must contain exactly 4 permutations, because you are constructing an isomorphism between them. So those permutations are nothing but, namely, F1, F minus 1, Fi, F minus I. Why I have written like this? Because in the theorem proof, you can observe that the permutation group G dash is defined in such a way that for every element in the group, corresponding permutation you are taking here. So if 1 is the element, corresponding permutation is F1. If minus 1 is the element, corresponding permutation is F minus 1. Like that, you need to take the permutations in the respective group G dash. Okay? Are you clear? So in this problem, G dash is simply F1, F minus 1, Fi, F minus I. Now the question is how to write the permutations here. Please understand, permutation is nothing but a bijective function on the set itself. So you are pairing the elements of G to the elements of G only, not in a different set. Okay. So if you observe how the permutation is defined in the theorem, Fa of x is equal to Ax. So whatever the permutation you are writing, you are multiplying this value with this A. So here F1 is nothing but the elements in G are 1, minus 1, I minus I. The suffix element is 1. You multiply all of them with this 1. So 1 into 1, 1, 1 into minus 1, minus 1, 1 into I, 1 into minus I, minus I. This is F1, nothing but the identity permutation. If you want F minus 1, 1 minus 1, I minus I. The suffix element is minus 1. You multiply all of them with minus 1. So minus 1 into 1, minus 1. Minus 1 into minus 1, 1. This is minus I, this is I. So if you want to the permutation Fi, this is 1 minus 1, I minus I. So multiply each and every element with I. So I minus I, minus 1, 1. Are you clear how we are making the permutations? Everyone, any questions? So, to prove that given groups are isomorphic, define phi from G to G dash by phi of A is equal to FA. Therefore, phi is an isomorphism, hence the given groups are isomorphic. So, the new group G dash, what you are forming here, we call with the name that it is called as regular permutation group. So the group what we have constructed here, we call that with a name, it is called as regular permutation group. So if the question is given that find the regular permutation group which is isomorphic to G, you have to proceed like that. Okay? Is it clear to all? So you can take one more interesting problem, then we can conclude this part. Shall I erase this? All right. So let me say, if G is the set taken by identity, value x, value y, and value xy. And further, it is given that x square equal to y square equal to identity, and now the question is find the regular permutation group. Find the regular permutation group. So here we follow the same procedure in constructing the respective permutation group. Since G contains 4 elements, you need to get the new permutation group G dash having exactly 4 permutations, nothing but Fe, Fx, Fy, and Fxy. And now let us calculate the values one after the other. So here Fe is nothing but so you are multiplying each and every value with E. Since E is the identity element, the same values will come as a result. So if you want Fx, so this is nothing but x into E, x into x, x square, this is y, x square y. So nothing but, so x square is E in the problem, this is xy as it is. Since this is E into y is nothing but y. Clear? How it is formed? Similarly, you can find the other also. I will write the last permutation. Fxy if you consider. So xy, so xyx, xyy, xy, xy. This is the actual thing you need to write Now you can modify them as since xy is equal to yx, you can write it as yxx, and this is xy square. Again, you can write it as x square y square. Since x square is equal to e, so this is nothing but y, this is x, this is e. This is the permutation you will get at the end. Since it is given that xy is equal to yx, I have make use of this thing here. Otherwise, you cannot build the permutation here. Please understand. You cannot simplify in this manner. It will be something different. Okay? It is given the problem that xy is equal to yx and x square y square values equal to identity. If the values are not specified in the problem, you simply calculate the permutation. Don't simplify that. There is no need to simplify. Just write the values. That's all. So in this way, we construct the regular permutation group, which is isomorphic to the given group G. So please take a note of this, and then we start another interesting chapter, that is cyclic groups. After noting, please tell. So is it interesting for you? The results as well as the problems in this chapter? Right? So now we begin with the chapter cyclic groups. It is very simple thing. Suppose you take a group G. Let me say it's a finite group. And you take an element A in the group. Now what happens? As you know, every element will possess the order. So while raising the powers of A, you will get identity at some power. Accepted? So let me say order of A is equal to n. It means that A power n is equal to identity. So can you give one guarantee that while raising the powers of A up to the power n, is all the elements distinct or not? Or elements get repeated? So all the elements are distinct, because I will give the simple example. So if you take the group 1 minus 1 I minus I, here order of I is equal to 4, because if you consider the powers I power 1, I square, I cube, I power 4. So I power 1 means I square means minus 1, I cube means minus I power 4 is 1. See, all the elements are distinct. Accepted? Similarly, here also, if you consider the values up to that power, all these values, if you consider this into a set, this is called cyclic group. Indeed, we call it as a cyclic subgroup because you are considering only the powers of A, other elements are also there in G. So you are taking a portion of G. It contains only powers of A. Other elements are also there in G. So what is meant by cyclic group in general? So you are considering all elements which are obtained by one single value. So that we are calling them as a cyclic group. Clear? Now, here we discussed about the cyclic subgroup. Cyclic group is nothing but if the group, the whole group what we have taken is generated by an element, then we call it as a cyclic group. The simple example is here, you can consider that here I generates the whole set. You can observe that I power 1, I square, I cube, I power 4. All the values have come. This whole set is generated by the element I. Accepted? Because while raising the powers of I, you will get all the elements in that group. So we say that the group G is a cyclic group and it is generated by the element I. So I is called generator and symbolically we will write like this. This is the symbolic notation. One interesting thing you can observe is the order of the group and order of the generator both are same. Did you observe? G contains 4 elements. So order of the group is nothing but 4. The element I also has same order. So whenever the element and group has same order, we can say that it will become the generator of the group. Okay? Did you get the logic? So the group order and generator order both are same, provided if it is a cyclic group. So group order is equal to generator order. Here generator means the element which is generating the whole group. You can talk about the finite case as well as infinite case. Both are correct. Now I say one more thing that based on cyclic groups, so many other results are also framed. Now the question is, if I know the order of the group, then can I calculate how many generators it will have? So if I know the order of the group, then how many generators it will have? There is an interesting question for us. Now let us discuss on this. Let me say I have taken the group with n elements. Now the question is, generally every composite number you take, we can write it as the product of primes. Accepted? You can write a prime factorization for it, for every number. You can write the prime factorization. Let me say n is equal to 36. You can write it as 4 into 9, nothing but 2 square into 3 square. This is the prime factorization. Accepted?
So for every number, you can write the prime factorization, the positive numbers you are talking about. So here there is a formula for this, that it will have phi of n generators. So what is this phi? Phi is called Euler function. So whenever a number n is given, how to calculate phi of n? Let us discuss now. Now the case is, so for the number 36, this is the prime factorization. In this, you exclude the powers, consider the prime numbers only. Here 2 is a prime number and 3 is a prime number. So what happens? Phi of 36 is equal to 36 into 1 minus 1 by 2 into 1 minus 1 by 3. So whenever n is written in the prime factorization, p1 power alpha 1 into p2 power alpha 2 into so on, pm power alpha m. So phi of n is defined as n into 1 minus 1 by p1, 1 minus 1 by p2, so on, 1 minus 1 by pm. This is the formula. To calculate phi value, we use this formula. And phi is called as Euler function. So can you say what is the value of phi of 36 there? By simplifying that value? Well, right. Now actually, the definition of phi is defined in a different manner. The actual definition is given that phi of n equal to the number of positive integers less than n and which are relatively prime to n. This is the definition of phi of n actually. The Euler function is defined in such a manner. For example, if you take the small case that let us say n is equal to 6. Now what are the positive integers which are less than n is nothing but 1, 2, 3, 4, 5. Among these values, you consider which are relatively prime to 6. So GCD of 6 comma 1, 1, GCD of 6 comma 2, 2, GCD of 6 comma 3, 3, GCD of 6 comma 4, 2, GCD of 6 comma 5, 1. So relatively prime is happened for two values. So phi of 6 is nothing but 2. Okay? Are you clear how phi is defined actually? The number of positive integers less than n and which are relatively prime to n. But the question here is, if you take 10, 20, 30, 100, it is okay. But if you take 1000, 2000, then it is very difficult using the definition. So there, this formula is derived. How to calculate phi of n? As in when you write the prime factorization, excluding the powers, you take only prime factors and use this formula, which gives the total number of generators for that cyclic group. So please take a note of that. After noting, please tell. Any questions, any doubts for anybody on this context? Yes or no? Is it noted? You can apply the same technique. So this thing you are asking, right? So you simply calculate GCD. GCD of 6 comma 1, GCD of 6 comma 2, GCD of 6 comma 3, GCD of 6 comma 4, and GCD of 6 comma 5. If GCD is 1, we call them as relatively prime numbers, isn't it? So how many relatively prime numbers are there? There are 2 numbers are there. So phi of 6 is nothing but 2. So you can imagine like this. Suppose if you are calculating, say I have given n is equal to 20. So what you are doing? You are going to take the numbers 1, 2, 3, 4, 5 up to so on 19. And you calculate the GCD. So GCD of 20 comma 1, what it is? GCD of 20 comma 2, what it is? So on. GCD of 20 comma 9, what it is? Among these, you pick up those values whose GCD is 1. And you count how many such values are there. 3 values, 4 values, 5 values. That we are calling it as phi of n. As per the definition, the number of positive integers less than n and which are relatively prime to n. Since every time doing like that is very difficult for taking n as a big number, so for that prime factorization technique we will use, which is very convenient to give or calculate the phi of n value. Okay? So you are just calculating how many generators are there, but you are not calculating the generators. What value will become a generator, that you are not actually calculating. You are just simply understanding that since G contains 6 elements, it will have 2 generators. If G contains 4 elements, it will have 2 generators. Like that you are thinking. Okay? You are just identifying how many number of generators it will possess. That's all. You are not at all calculating the generators. Please understand. So, I will give one more interesting thing, that if you know one generator, you can determine the other generators also. I will say, if A is a generator, then A inverse is also a generator. Because for the group 1 minus 1, I minus I, see, I is the generator. Because I power 1, I square, I cube, I power 4 will give the given set. So what is the inverse of I here? Minus I. So the same set is generated by minus I also. So it is nothing but you can calculate minus I whole power 1, minus I whole square, minus I whole cube, minus I whole power 4. The same set will come. Please check. Check on yourself and confirm the answer. So if A is the generator and A inverse is the other generator, is it clear to all? Fine. Now there are some small results are there based on this cyclic group concepts. So one thing is, every cyclic group is abelian. Second, a group of prime order is cyclic. Third, every subgroup of a cyclic group is again cyclic. Another one, order of the group is equal to order of the generator. You take a note of them. Every cyclic group is abelian. A group of prime order is cyclic. Every subgroup of a cyclic group is cyclic. Order of the group equal to order of the generator, whether you can take the finite group or infinite group, whatever the case. So if you take the group is finite, so you will have an element which has finite order. If you take infinite cyclic group, you will get an element whose order is also infinite. For example, the simple example is z comma plus. So here the number 1 generates the whole group z, because you keep on calculating multiples of 1, 1, 1 plus 1, 1 plus 1 plus 1, so on, you will get the whole group z. So z comma plus is a cyclic group where the generator is 1. So please understand that here a power n, we discuss, let me say, generated by a means the whole set is nothing but in powers of a. So generally we talk of the operation as multiplication. If you take the operation as addition, here a power n means n into a. So you are adding a n times. So for negative numbers, you can take 1 power minus 2, nothing but minus 2 into 1. 1 power minus 3, nothing but minus 3 into 1. Like that you are doing. Okay? So for z comma plus, 1 is the generator. So at this point, I want to conclude our today's session, and the next class we are going to meet, which has 3 generators. Why not? Now you take the example phi of n is equal to 3. Can you give a number for that? So here we need to understand that whenever an element is a generator, its inverse is also a generator. So in such case, if you want to get 3 generators, by default, one element must be self-invertible. The inverse is itself. Then in that case, you will get 3 generators. Please understand. Because let me say, if phi of n is equal to 3, that will come for what number? You need to understand. that maybe you can take the case of matrices, permutations, etc. There you can find. Okay? Because generally generators will occur in even numbers. Because if A is the generator, A inverse is also a generator. So generally you will get the number of generators as 2, 4, 6 like that. Unless the element is self-invertible, you will not get 3 generators. That's the issue here. Any other questions, please? Right? So let us stop here. Yes, I and minus I, it has only 2 generators. Because you can calculate phi of 4 value. Phi of 4 is equal to 2. Because 4 is nothing but 2 square. So phi of 4 is equal to 4 into 1 minus 1 by 2. So this is equal to 2. So you will get 2 generators only. As per the formula. So are you feeling that you will get 3 generators for this set? Okay, right. So phi of n will give the idea that how many generators you are going to get. In fact, you can observe one more thing, that if the number what you have taken is a prime number, let me say you take phi of 5, the value is nothing but 4, because 5 is a prime number. So every number which is less than 5 is always relatively prime to 5, because GCD of 1 comma 5 1, GCD of 2 comma 5 1, GCD of 3 comma 5 1, GCD of 4 comma 5 1. So you will get 4 generators. So if you calculating phi of p, where p is a prime number, it is nothing but p minus 1. That is the interesting issue you can observe. So if n is a prime number, the group order, you will get p minus 1 generators. Any other questions, please? Anybody? So you can expect many of the questions on cyclic groups, especially with regard to exam point of view. And observe one more thing, that there is an interconnectivity between cyclic groups as well as isomorphisms. Let me say, I have taken that G is a group which is isomorphic to another group, say A. So if G is cyclic, this is also cyclic. Now the interesting thing is, if you say that for this set A is the generator, for here corresponding image f of A is the generator. So G is generated by A and A is generated by f of A. So isomorphism preserves the structure as well as the cyclic nature of the groups. That is one interesting thing we need to understand. So you can have the interconnectivity between homomorphisms, cyclic groups, permutation groups, etc. in the upcoming sessions. Okay? Right? So that's all for today. And I wish you everyone a very happy and prosperous new year. And we will meet in the next session. Thank you very much.